Hey there, folks. Good morning. For today's problem, we have this adventurer named Exena the Exterminator who's being chased by a dragon down a castle hallway. To escape the dragon, she flees into a nearby room and shuts a massive door behind her. Our job is to figure out how long it takes her to close that door. Let's begin with a picture. We're given the door's height and width and told that the door is initially perpendicular to the wall, which means closing it requires a torque. Since our picture is three-dimensional, we need to be a bit more specific about what torque we're referring to. To help with that, let's add a coordinate system that's centered on the hinge of the door. This will make the z-axis our axis of rotation. In the problem description, only two forces were mentioned. The weight of the door, which I'm drawing from the door's center of mass, and the force that Exena applies along the door's edge. Neither of these forces have a line of action that goes through the axis of rotation. That means both of them will produce a torque. But only one of those torques is responsible for closing the door. The question is, which one? Now, it might be obvious which force will make that happen, but just claiming that something is obvious is not a very good explanation. What we should do is demonstrate proof why one force works and the other doesn't. To do that, we're going to upgrade our definition of torque to a vector cross product. Let's apply this new definition to each force, starting with the door's weight. Here I've introduced a weight vector and inserted that into our torque definition. The other piece that we need is the r vector, which is a position vector that points from the axis of rotation to the force vector, and that will be located here. In order to use these vectors in our new torque definition, we also need to know what their components are. Thankfully, in this situation, it's pretty easy. The position vector points purely in the plus y direction, and it has a length that's equal to half the width of the door. Thus, its components will look like this. The weight vector points purely in the minus z direction, with a length that's equal to the door's weight. So its components will look like this. So now we've located our vectors and figured out their components. The next step is to actually perform the cross product. This requires a technique from linear algebra known as solving for a determinant. And if you're not familiar with what that is, that's okay. Here's a very simple walkthrough of how to do it. First, we're going to create a table with a column for the x, y, and z components of our vectors. The position vector comes first in the cross product, so its components will go into the first row, followed by the weight vector in the second. Since our cross product is also a vector, we need to use this table to figure out its components and then string them all together. For the x component, we start by ignoring what's listed in the x column, and we're going to focus on the other two. Let's multiply this component by this one, as well as this component by this one. If we take the red result minus the blue result, we get the x component of the cross product, which, after simplifying, will look like the following. So our x component is done, and now we can bring the x column back into focus and ignore the y column next. This time, we multiply this component by this one, and this one by that one. Like before, take the red result minus the blue one, and then simplify it to get the y component. Let's move on and ignore the final column next. Our red product will come from these two cells here, and the blue product from the other two. Taking the difference of the red result and the blue result, we find that our z component will simplify to 0 as well. And at this point, we now have our full torque vector that's due to the weight of the door. Notice that it is not in the rotational direction that we're looking for. This torque wants to rotate the door counterclockwise about the x-axis. And that motion can't close the door. We need to rotate it about the z-axis to make that happen. So this concludes our proof that the weight vector is the wrong force to use here. And with that out of the way, we can go through this process one more time using the force applied by Exena. I'll replace it with a force vector and insert that into the torque definition. The position vector for this force will cover the entire width of the door, which means its components will now look like the following. As for Exena's force, that vector points purely in the plus x direction, so we can write out its components like this. Next up is the cross product, and the process is exactly the same as we just did it, except now there's a different vector in the second row. Since we know all the steps to this process already, I'll save us a bit of time and jump straight to the end. The resulting torque corresponds to a clockwise rotation about the z-axis, which is exactly what we're looking for. It matches up with everything in our picture. Now we're ready to move on to the sum of torques equation and use what we just obtained. About the z-axis, we only have a single torque, which is due to the force that's applied by Exena. Since it causes a rotation in the negative rotational direction, we have to add a negative sign over on the right-hand side as well. Instead of eliminating these negative signs, let's just hang on to them for now and insert the definition for our torque on the left-hand side, like this. From here, the goal is to isolate the angular acceleration variable and use that in a rotational kinematic formula to solve for a time. To do that, we're going to need a moment of inertia expression first. And unfortunately, there's no option in our table resembling the shape of a castle door. But that's okay. We can approximate our castle door using option D here and just treat it like a thin rectangular plate. Thus, our moment of inertia expression will be this one here, 1/3 ma squared, where a represents the width of the plate. And since the width of the plate is the same thing as the width of the door, we can go back to our equation and insert that moment of inertia expression using W instead of A. From here, I'm going to multiply both sides by 3 and divide both sides by mw squared. We end up with w upstairs and downstairs. So let's cancel out a single factor of it, which will simplify to the following. We now have our angular acceleration, so let's take a look at this kinematic equation next. We know that the door wasn't initially rotating, so this term can be thrown away. The initial angle of the door is 90 degrees, and the final angle will be 0. So we can do away with this theta final term as well. Let's move theta initial over to the other side and then insert our negative expression for alpha. At this point, we can safely cancel out the negative signs and simplify. Recall that these rotational kinematic formulas require units of radians for the angles. That means we need to replace our initial angle of 90 degrees with the radian equivalent, which is pi divided by 2. This results in both sides containing a 2 in the denominator. So let's go ahead and cancel that out and simplify what's left. If we multiply both sides by mw and divide both sides by 3 times Exena's force, we can isolate t squared and then take a square root of both sides. We now have our time and everything is ready. All that's left is to just plug in our numbers. When I do that, my calculator says that it takes Exena approximately 0.675 seconds to close the door behind her. That is our final answer. And as always, thanks for watching.